Hello, my name is Sean Hum. I'm a professor in the Electrical and Computer Engineering Department at the University of Toronto, and it's my pleasure to be here today to tell you about how we're embedding the Keysight Smart Bench Essentials package into a second-year hardware design course. Here's a bit of background on that course. It's entitled ECE 295 Hardware Design and Communication. And working in teams, students will acquire a number of skills. First, students will learn about agile methods in hardware design, and using those methods, design an entire electronic system from the ground up. Using computer-aided design tools, students will engage in the design of a practical hardware system, beginning with schematic capture and laying out their circuit using a computer, and then it will translate that into a printed circuit board layout, which can eventually be fabricated. When students get their printed circuit boards back, they will be responsible for populating them and assembling them. They'll learn how to solder these boards together, and in the process become familiar with surface mount technology, electrostatic discharge handling, and so on. Here's a photo of the Mayor of Toronto, John Tory, learning how to solder at a recent hackathon at the University of Toronto. And we always tell students if he can learn how to solder, so can they. An important component of their experience will be testing their systems with state-of-the-art measurement equipment. Part of that also means that students will learn about test automation, which is an extremely important skill that industry is expecting of our graduates. We see this as a very important component of the course where students will learn to master practical aspects related to test and measurement. Even something as simple as triggering a scope can take many sessions of practice with students, and this is something that we hope students will be able to do after leaving this course. As such, the labs are really key to enabling this experience. And to support this course, we're actually developing a brand new open access laboratory in which students will design, develop, build, and test their hardware projects. This lab is embedded in the MyHall Light Fabrication Center at the University of Toronto, and that center supports students with a variety of resources. They have hand tools available to them, soldering stations, fume hoods, 3D printers, and so on. And within that facility, we will also have benches set up with all the instrumentation that we'll need to test their designs. This facility was specifically designed as a teaching laboratory for experiential learning for this course and can be potentially used by other courses as well. Our core idea in developing this laboratory was to provide students with anytime, anywhere testing capabilities similar to what their peers in software enjoy. For example, a student developing software can basically code anytime and anywhere they wish to, and we want to bring that same experience to students developing hardware. To provide this anytime, anywhere capability, this lab will be open 24 hours a day and accessible by students via a card key system. The instruments will also be remotely accessible, meaning that students could set up experiments on the bench and be able to remotely test them anytime they wish. In developing the lab, we faced a number of instrumentation choices. At each bench, we originally wanted the following items. We wanted a high-speed digital storage oscilloscope, and we wanted some sort of multi-channel measurement capability for voltage and current measurements. Originally, we were thinking multiple digital multimeters could fulfill this purpose, or some sort of sophisticated multi-channel data acquisition system. Of course, we need a power supply to power circuits, and for stimulating circuits, a waveform generator. Here's a list of items we originally thought of populating each bench with. Around the time that we were putting together this wish list, we learned about Keysight's upcoming Smart Bench Essentials package. And actually within that package, there were 4 instruments that satisfied all of our requirements, and they're shown in this half of the table. What's important is that these instruments not only satisfied all of our requirements, they could do so at a much reduced cost compared to our original choices. And in some cases, we're even providing more capability than our original instrument choice. For example, the function generator, which was the 3351B, originally only has 1 channel, whereas the educational version in the Smart Essentials package actually has 2 channels and costs significantly less than the original generator. With all the savings, we're able to complement the lab with additional test pieces that students could have access to, including a high-speed mixed signal oscilloscope, a vector network analyzer for RF measurements, thermal imaging camera for measuring temperature, and a multi-channel data acquisition system for more comprehensive measurements. In developing this lab, a very important theme was also the physicality of the lab. There's been a significant move towards virtual laboratories and instrumentation recently, but we really wanted to have a bench for students to be able to test their designs. We feel like students need this experience despite the proliferation of these virtual lab products. And there's this notion, not only in our university, but also from companies that hire our graduates, that true ECEs touch hardware. Those same companies are expecting our graduates to have hands-on experience in hardware and testing. In addition, we wanted to foster a greater maker culture at the University of Toronto, support a variety of student activities. There are extracurricular clubs on campus that are developing anything from solar-powered vehicles to CubeSats to embedded IoT devices, and this lab will be essential in supporting those students' efforts as well. Collectively, we believe these factors are helping draw students not only to the facility, but to the ECE 295 course itself. And we feel like the Smart Bench Essentials package is also helping us directly address our goals. I've had the chance to play around with the Smart Bench Essentials package. It comprises those 4 instruments I listed earlier, and you can see it set up behind me here. This is the 5.5 digit digital multimeter here. This is the triple output programmable power supply. This is a 2-channel waveform generator, and below that, the digital storage oscilloscope. In assessing the test equipment in the Smart Bench Essentials package, I've discovered a number of features that I think will be very useful for students in debugging their systems on the bench. For example, the scope has a built-in function generator, which gives students another option for stimulating their circuit. Since that function generator can internally trigger the scope, it eliminates the need for some extra cables on the bench. But more importantly, the scope has a built-in frequency analysis tool, which allows the scope to automatically sweep the frequency of the function generator over a predefined range and make measurements of the magnitude and phase response of the circuit, essentially producing a Bode plot. This could be very useful for students that want to very quickly assess the frequency response of their circuit on the bench. The digital multimeter is also very capable. It has a data logging feature built in, which allows students to program data acquisition over a long period of time at a predefined interval, which can allow students to check their systems for drift or changes in temperature and so on. The digital multimeter also has a very handy feature. I mentioned earlier that we were interested in multi-channel measurements at the bench, which we were originally going to support by having multiple multimeters at the bench. But this particular multimeter actually has a second channel on it. For example, you can measure DC voltage and AC voltage at the same time. For example, if you want to measure ripple on top of a DC signal. Or in this example here, you can see that the multimeter can be configured to make a simultaneous DC voltage measurement and a DC current measurement at a point in the circuit. This is a very useful feature as well that eliminates the need for a second multimeter. I've also found the modulation capabilities of the function generator very useful. Students are just starting to learn about communications at this stage of their career, and this function generator gives them the capability to synthesize a variety of signals and see how information can be modulated onto a carrier signal. I found the power supply to be very cost-effective and well-provisioned. There are 3 outputs, as I mentioned earlier, and significant current carrying capability on each output. Finally, I find the Smart Bench Essentials bundle a great all-round package. The instruments fit together very nicely in this cool aesthetic that you see behind me. There's even a mounting bracket that eliminates the need for us to develop a custom solution for housing all of the instruments. And I think it just looks great. I think this would be very attractive for students to use, and I'd like to have one of these myself. So I'd like to thank you for your time. I hope this short presentation has been informative in helping you learn about how the Smart Bench Essentials bundle can be embedded into an educational environment. And certainly if you have questions, please don't hesitate to reach me at the email address you see listed here. Thank you.